Okay, good morning to everyone present. I welcome you all for the fourth day program of the 6 day online faculty development program on electric vehicle breakthroughs and challenges. So before we start the program, once again I repeat to the participants that at least 80% of attendance is required and feedback form should be filling is mandatory for all the sessions you are attending, and final assessment will be conducted on the last day 20th December. The final assessment will be conducted, so all the participants must attend the final assessment. Okay, so if now formally start the session, I welcome you, sir, Dr. K. Ramash Kumar. So regarding the resource person profile, he received the BE degree in Electrical and Electronics Engineering from University of Madras in 2002. He did his MTech from Pondicherry Engineering College, Pondicherry in 2005. And he received his PhD degree from the Department of Electrical and Electronics Engineering, Jawaharlal Nehru Technical University, Hyderabad in 2014. So he has 21 plus years of teaching experience in reputed engineering colleges. Currently, he is working as a professor with the Dr. NGP Institute of Technology, Coimbatore. He has authored more than 100 plus papers published in national and international conference proceedings and professional journals. He has published 4 book chapters as the author. He has published 3 national patents. He received funds from various government, non-government agencies such as CSIR, AICTE for organizing conferences, seminars, product developments and projects. He received seed money from research project from the management, Karpavam College of Engineering, Coimbatore, Tamil Nadu. His research interests include classical controller design for DC to DC converter, Leo converters, resonant converters, power quality, modeling of power converters, high power factor converters, and multi-level converters. He received the Kalpa Acharya Award, the best researcher from BEEA 2021 CSR Professional. He regularly reviews articles of IET Power Electronics, International Journal of Power and Energy System, elsewhere, Electric Power Component and Systems, Taylor and Francis, International Journal of Power Electronics, WASET, International Transaction on Electrical Energy Systems, Wiley, Transaction on Circuit and Systems Control System, IEEE transactions on industrial electronics, and IEEE transactions on power electronics. He is an active member of the professional societies IA Engineering, ISTE, IRED, and ISRD. He is an editorial board member and academic editor of the International Journal of Electronic Engineering Research, Research India Publications, Mathematical Problems in Engineering, Wiley Publishers, Journal of Electrical and Computer Engineering, Wiley Publisher, PLOS 1, Scientific Reports, Springer Nature, and Open Journal of Engineering, Research and Technology. So, once again, I welcome Dr. K. Ramash Kumar for the 4th day program of the 6 days online faculty development program on electric vehicles, breakthroughs and challenges. So now it is over to you, sir.
Okay, thank you, sir. Thank you for my introduction. First, I would like to thank management, principal, and the coordinators of Ali Muhammad Salih College of Engineering for choosing me as a resource person. Now I move on to the today topic, multiport power converters for electrical vehicle applications. So as per the electrical vehicle concern, we have a different components, like start from charging station, and we have different types of charges, on-board charges, off-board charges, and then we can have a battery, and the next component is DC-DC converters, and the inverters, and the electric motors, and we can have a control unit. So we have a battery management systems. So these are all the main component of them. electrical vehicle. But I'm going to focus on the one of the part of the EV applications, like how to charge the EV batteries by using a single converters. So that is the topic I framed as a multi-port converter for EV applications. First, what is multi-port converter is we can have a different combinations. First combination is a single input and dual output or multiple output. Then multiple inputs and a single output or multiple input the multiple output. So this combination of circuit we are going to call as a multi-port converters. So now we move on to the just to look at the slide here. In the slide you have a block diagram. I already mentioned what are all the main component involved in the um, electrical vehicle. As per the electrical vehicle concern, you have a charging station, and again charging station is connected to onboard charger. Then onboard charger we are also called as a AC charger. Then here we have a AC to DC. Then again you have a DC-DC converters. Then again it is connected to the high voltage battery. For example, 280 volt DC to 800 volt DC, for example. Then within this battery pack itself, you have a BMS also, battery management system. We can monitor all the battery parameters like battery voltage, current, temperatures, SOC, cell voltage, then SOD, everything we can monitor by using a battery management system. So now here onboard charger, inside a onboard charger, you have a AC to DC converter, and then afterwards you can have a DC-DC converters like maybe boost converters. Then again it is connected to the high voltage battery. Next, again you have a one more DC-DC converter. In onboard charger itself, you have one DC-DC converters. Next, one more DC-DC converter is also there. Again, these high voltage batteries used to drive the motor through our inverters. Next, one more DC-DC converter is available here. The purpose of this DC-DC converter is we have to step down the high level voltage to low level voltage, like maybe a 12 volt. Here, one more battery is also available inside the EV. The voltage range is a 12 volt. So these 12 volts we are going to charge by using the again one more DC-DC converter we are going to use. Step down the high voltage to low voltage. This 12 volt is connected to the low power accessories inside the electrical vehicles. So as per the electrical vehicle concern, there are two batteries are connected inside the vehicle. One is used to drive the motor, like through inverters, or some manufacturer they are going to use for the DC-DC converter. Next, followed by the inverter. Then again they are going to connect for the motor. Some manufacturer they are going to use for the battery directly connected to motor through our inverters. So depending upon the manufacturer, it will also, like the structure is also vary. Similarly, some manufacturer they are going to fix the wheel in a rear wheel. Some manufacturer they are going to fix the rear wheel, the back side. Or so that are both combination. That entirely depends upon the manufacturers. So next, here one more battery is used to power for the internal accessories of the electrical vehicle, like maybe a speaker, um, uh, uh, we can use for the low power voltage or low voltage. So now, what is the main drawback in this concept is when you use for the separate converter for charging of low voltage battery and a high voltage battery. So this will lead to more switching losses. And then once if you have a more switching losses, not only that you have more number of components like diodes and inductor and switches. So now again you have device losses, again component losses. So again, switching losses. All put together, you have a more losses. So in order to overcome this problem, so what we have to do means we have to integrate the two converters into the single topology. So that concept we are going to discuss now. Okay, so now in existing, I already pointed out, in existing electrical vehicles, we are going to use for a separate DC-DC converter. One is used for a low voltage battery charging purpose. Another one is used to charge for the high voltage battery. So high voltage batteries used to drive for the motor via inverter, and then low voltage is used to charge the battery. Again, it is connected to the low power accessories for the internal inside of the electrical vehicles. Now, so we need to, so suppose this is the existing circuit, so separate converter we are going to use. When you use this concept, what will happen? We are facing a problem of ripples, output voltage ripples, and the size and weight, because when you use for the separate DC-DC converter for charging of two batteries, so what will happen? The size and weight also increases. So, and more switching losses and more number of components, device losses. So, this will also affect the performance of the electrical vehicles. So, we need to overcome this problem. So, what is the solution? What is the solution is we can go for the multi-port DC-DC converter for charging for the EV battery. So, now I have done some of the analysis here. So there are different topologies for multi-port converters are available. So here in the maybe first one of the paper, maybe one of the multi-port converter. The structure of the multi-port converter consists of maybe two switches, three capacitors, three diodes, two inductors, two outputs. The single input, the output is two. So it is comes under for one of the topology of multi-port converter structure. So what is the voltage transfer? There are two outputs. So therefore, one output is we can use it to charge for a high voltage. That means one output means one output is connected to high voltage battery for charging. Another one more output is connected to the low voltage battery charging. So now here, what is the voltage transfer gain for? Voltage transfer gain means the ratio of the output voltage to input voltage. So now we can express in terms of duty cycle. So the first multi-port converter, the boost converter or step-up converter, one of the output voltage transfer gain is 2 minus 1 divided by 1 minus D2. Then again, V2, it is another output voltage transfer gain, D1 minus D2 divided by 1 minus D2. So this is the low voltage output voltage transfer gain. The first G1 is a high voltage output voltage transfer gain. So what is the efficiency is 98% for this topology. Similarly, the second topology, we have a number of switches 2, number of capacitors 6, again number of diodes are 6, number of inductors are 2, and again number of output is also 2. Again, the relation for voltage transfer gain for high voltage output and similarly for low voltage output. The second topology has produced the efficiency of 93.98. Similarly, I have surveyed for the recent articles. So now the efficiency varies from 94.22 or 92 varies from 98%. Now I have developed one more um, multi-port converters. I have integrated the boost converter. I am integrated the buck converter. So now I can propose that positive output boost converter integrated the buck converter. In short form, we are represented as a POPCI PC. So positive output boost converter integrated buck converter. So I'm going to integrate the whatever the problem we are faced in the existing EV application of DC-DC converters. We are going to use for a separate DC-DC converter for charging of low voltage and high voltage. Now we are going to integrate. After integrating the two converters into single topology, so we can achieve for the good efficiency, reducing the switching losses, and the ripple voltage also minimal value. Then we can reduce the size and weight. So naturally, what will happen? The performance of the EV also improved. So now our proposed circuit is number of switches are two, capacitor is two, diode is 2, inductor is also 2, then output is also 2. The first voltage output of voltage transfer gain is boost converter 1 divided by 1 minus D2. The second one voltage transfer gain output is D1 minus D2 divided by 1 minus D2. So the efficiency of this proposed converter is 99.39. So now, so this is the structure of our proposed circuit. So now in the proposed circuit, just look at the circuit here. This is the supply voltage V in DC voltage. This is the inductor L1 and then switch S1 and diode D1 and capacitor C01 and then one of the load I am represented here R01. So instead of this R01 load, you can connect for the high voltage battery. So this structure indicates for a boost converter. Now we are going to integrate it into like a buck converter concept here. So we have a switch S2 and again a L2 and a D2 and a C02 and a R02. So this structure is a buck converters. So we are integrating the boost and the buck. Now we are combined the two circuit into single circuit. So now we are minimizing the number of component, also the size and weight, everything is going to be reduced. Now here the R02 is one of the load resistance here. So now in the R02 you can connect for the low voltage battery. So there are two loads are here, single input, two outputs. One of the output is R01. Here you can connect for a high voltage battery. Then here R02 you can connect for the low voltage batteries. So now move on to the working of this circuit. So before start of we have a four mode of operations for the proposed circuit, like positive output boost converter, integrated buck converter. This is also one of the topology of the multiport converters. So before start of the mode, in the previous mode, the L1 is stored the energy. So before we are going to start the mode 1 operation, this L1 is in the previous mode, it is fully charged. Now we move on to the mode 1. In mode 1, we are going to turn on the switch S1 and turn off for the S2 switch. So what will happen? The input voltage and the previously stored energy in the inductors, again it releases when we are going to turn on the switch S1 and then open the switch S2. Now again supply voltage, then again inductors start to decrease the energy. Again it goes to the switch S1 and again L2. Now the L2 start to charge. Again capacitor also start to charge, again return back to the supply voltage. Then here the diode is, now the diode here you have diode is in reverse bias conditions. Here the capacitor is releases the energy through the load here. Now it is discharging, start to discharges. Next, again in mode 2, we are going to close the both switches, S1 and S2. So now in the previous mode, L1 is fully releases the energy. Now the L2 and the C02 charges through our supply voltage. Next, we are going to turn on the S1 and S2. So what will happen? Now the inductor start to charge up to the supply voltage. Now V in is connected to the circuit. Here again, still the capacitor is again here discharging. So therefore, the potential available at the output side is higher compared to the anode of the diode. Therefore, the diode again still in reverse bias conditions. Next, now the inductor start to store the energy up to the supply voltage. Again, here there is here this is short circuit. Again, the L2 again capacitor again it is also like this is the direction. The releasing the energy. Next, we move on to the mode 3. Again, mode 3 and mode 1 again same. In mode 3, again we are going to open the switch S2 and turn on the S1. Again, the stored energy in the inductor L1 again releases, again start to charge the L2 and C02. Then this is the mode 3. Then mode 4, we are going to open for the switches S1 and S2. Now the inductor and then the input voltage, then added again. Now the capacitor is fully discharged. So therefore diode D1 is start to conduct because the anode is high potential with respect to cathode of D1. So therefore start to conduct. Then again the input voltage, inductor energy again connected to the load. Now the capacitor C01 is start to charge. Similarly here the freewheeling diode here. So the inductor L2 and again start to discharges through this again load and capacitor again through this diode, freewheeling diode. So this is the working of the proposed multi-port converter circuit. Now we move on to the mathematical analysis. So now we have to do for the when the switches are on and off during that particular time period, the inductor L1 is start to charge and then start to store the energy. That means increasing the current. And when we are going to turn off the switches, the inductor start to decrease the current. So equating the voltage second balance of inductors. So now we are going to express the equations. So that is the boost converter expression here. So now when we are going to turn on the switch, what will happen? The inductor start to increase the current. So therefore D2. So D2 means here when this inductor start to charge S2 is turned on, so that time the inductor is start to increase the current or store the energy. So therefore we express here D2. So when the inductor start to decrease is we can have here like during the off time of the switch S2, during the off time of S2, then the inductor, so the inductor is start to decrease. So now we are going to equating this expression during the on time of S2. So now the inductor is start to charge. So therefore we are written as a duty cycle is D2 is a duty cycle of the switch 2, D1 is a duty cycle of the switch 1. So now we are going to equating the expression. So D2 is inductor current is rising. So when 1 minus D2, when the switch S2 is off, the inductor start to decreases. I already explained in the work. So now when S2 is open, the inductor previous stored energy again releases. Now the L2 and the C0 is charges. So now you can write down the mathematical relations. After equating this expression, then you will get the voltage transfer gain. So in the table I already mentioned voltage transfer gain for the one of the output. This is the step of high voltage output, or we can call it as a step up output or boost converter output. So V01 by V in is equal to 1 divided by 1 minus T2. So based on this duty cycle variation, we can also get a different voltages. So next one is another output that is called buck converters. So in the buck converter, we can have a different combinations. Again, we have a output V02. So see, the inductor current rises when switch D2 is on conditions. Here already I mentioned. So during the on conditions, the inductor current is rising here. So when during the off conditions, what will happen? The inductor current is decreasing. So now you can equate the expression. You can equate the expressions. Then you will get the output voltage for the buck converter. So V02 by Vns equal to D1 minus D2 divided by 1 minus D2. So next, what is the minimum and the maximum operating duty cycle here? Here we can operate from 0 to 0.9 and 0 to 0.9. So maxima I consider as a 0.9 duty cycle. We can also take 0.95 or 0.96. So after substituted in the formula, I will get the V naught variation. Voltage variation is V naught 1 and V naught 1 and V in relation is varies from when you take for a V into 10 times of V in. So that is the range we are going to operate for the uh, uh, one of the outputs. Similarly, for the another output is start from 0 to 0.8 percentage of the V in. That is second one. This is for the step down converter. The first one is indicates for the step up converter relations. Now here this is the simulated waveform. Simulated waveform of the proposed multi-port converters. Here the current ripples are very small here from the circuit, very clear here. So one is the IL1. So when the switch is on and off condition, the current is start to rise and then current start to decreases. This upper limit and lower limit we are represent as a peak to peak inductor current ripple. So now this is the very minimal value. So now here I have taken as some simulation parameter here. So duty cycle I operated for the two different ranges. One is from 0.6. Another one is for example D1 is duty cycle of the switch 1. For first case 1 I consider as a duty cycle is 0.6. The second case I consider as a zero point 0.3. Then in first case I can take D1 is equal to 0.6 and D2 is equal to zero point 0.3. Whereas in second case I consider as a D1 is equal to 0.9 and D2 is equal to 0.8. Then input voltage is 12 volt. So now V01 is equal to, when I consider as a case 1, D1 is equal to 0.6 and D2 is equal to 0.3. After substituted in the theoretical formula, I got the output voltage is 17.14 volt. Similarly, for V02 is 5.14 volt buck converter output voltage, and V01 is a boost converter output voltage 17.14. So now the case 2 I consider as D1 is equal to 0.9, D2 is equal to 0.8. For such cases, the output voltage V01 boost converter output voltage is 60 volt, and then output voltage of buck converter uh, it is a 6 volt. Now we are considered as a load values 25 ohm for R1, R01 and R02 is a 12.5 ohm. Similarly, based on the theoretical calculations, then the output current values for case 1 and case 2 we are calculated, and similarly for input also calculated. The efficiency values varies from 99.39 to then 89.78. So then inductor values and capacitor value and then ripple voltage also we assumed. So these are all the specification we are considered for the simulation purpose of the proposed converters. So now just to look at the simulation result here in case 1, we considered case 1 is D1 is 60 percentage and the second one is a 30 percentage for duty cycle. Now this is the gate pulses for switch S1 and this is the gate pulses for switch S2, and then the second one is indicated as a simulated output voltage for V01 and V02 and Vin. So Vin is we taken as a 12 volt input voltage, and then output voltage for a boost converter is 17.14, but there are small peak overshoot at the startup, but it will be settled very quick. Then again V02 also 5.14. So these values are exactly matched our theoretical value. So these simulated values exactly matched our theoretical values. So next, case 2. So case 2 is duty cycle is 90 percentage for a D1. Then second to D2 is 80 percentage. Again, this is the gate pulses for switch S1 and S2. First simulated result. The second simulator result indicates for output voltage. I already mentioned in the table, theoretical value for case 2 is V naught 2, 1 is equal to 60 volt, V naught 2 is equal to 6 volt. The say, whatever the theoretical value, again we are obtained in the simulated result. So here there is no overshoot for when you go for a more duty cycle. So now, but it takes more time to settle compared to the low duty cycle operation of the multi-port converters. Now coming to the, so this is the, these results indicates for there is no voltage stress because we are already mentioned when you go for a multi-port converter, there is no voltage stress, there is no current stress, di by dt and dv by dt. So now we need to show the evidence for the simulation result. So this is for the gate pulses for S1 and gate pulses for S2. When we are going to turn on for S1, so that time the just to see here the result voltage across the waveform, and again current the switch is on. During the on condition there is a current flow through the switches. So that time the voltages are zero because the switch is on conditions, it behave like a short circuit. So therefore the voltage zero. Again here there is during the off condition there is a voltage across the switches S1 and then current is zero. If you look at the voltage and current through the switches, voltage across the switches and current through the switches, there is no current stress. That means there is no overshoot or there is no transients for a current waveform, current through the switch. Similarly, for the voltage across the switch. So this will indicate there is no voltage stress and current stress. Similarly, switch S2 and S2, current through the S2 and then current voltage across the S2 waveform also, there is no voltage stress and current stress. And then inductor current is also minimum ripple because we are already mentioned why we go for these multi-port converters. There are some main advantages. One is a voltage stress, there is no stress, there is no switching losses. So now the inductor current are minimal, good efficiency. Okay, so now these are all the evident result. Now this is the simulated evident result. So inductor current is minimal ripple. So again here also minimum ripple. So output voltage also minimum ripple. So now there is no voltage stress, there is no current stress. Now again there are some experimental also we are carried out for these converters. So we can taken as a different analysis. So different load resistance. So let us take for the R01 and R02 for a 25 and 12.5 ohm. So the simulated value and the theoretical value we are mentioned here. Similarly for the ripple output voltage also mentioned here. So 99.39 and 98.49. The ripple output voltage is at 1.2 volt and then experimentally 1.6 volt. Then followed by the V02 output ripple voltage is 0.005 volt and 0.007 volt. Likewise, we are analyzed for a different load resistance variations like 50 ohm and 25 ohm and 100 ohm and 50 ohm and 150 ohm and then 50 percentage. So 50 percentage, suppose when you choose for the R0 to 1 is 25, we can reduce for the 50 percentage for R0 to. Likewise, we are taken as analysis part here for analysis part for the proposed converters. So this result indicates that the converter is having a minimum ripple for a different load resistance and also the efficiency is also maintained for a 82 to 99, 98 percentage the variation. So this is the one of the topology, right? So this is the one of the topology of the multi-port converter. Again, the same topology is applied to the normal converter. This is a normal boost converter and buck converter. So same concept is applied to the uh, super lift converters, right? Why we go for the super lift to loop converter is loop converter is also derived from the basic circuit like a boost converter and then buck boost converter. From the boost converter, buck converter and buck boost converters, So the loop converter also derived. So by adding of components like inductors and diodes and capacitors. So now, so now here superlift to loop converters. As per the loop, why we go for the loop converter is we can have a more gain. We can get a more transfer gain, voltage gain. We can also reduce the ripples. We can all get more good efficiency. So this is the reason we go for the loop converter. In loop converter also different techniques are there. Voltage lift technique, super lift techniques, ultra lift techniques. In voltage lift techniques, the output voltage transfer gain increases in arithmetic progressions. Like for example, if you have a basic circuit, you can add one more stage incremented by one. So this is the way we are going to increasing the voltage transfer gain in a voltage lift loop converters. Whereas in a super lift to loop converter, the output voltage transfer gain increases in a geometric propagations, like a power of the next stage. So this is the way we are increasing the output voltage transfer gain in a super lift loop converters. Now ultra lift converter is the combined characteristics of super lift converters and voltage lift converters. Now here I taken as one of the IEEE transaction paper. So now here you have a super lift converter here. So B in L1, diode D1, C1 and D2 and S1 and C01 and RL1 and the load. This is the high voltage output load. So this combination of component connected in the circuit. So now this is the structure for the super lift to loop converters. Now next to circuit is, so we have L1, sir. We have L1, S2, D1, C1, D2, C01 and load and input voltage. This is the structure of the loop converters, super lift. So buck converter is S1, D and L2 and C02 and RL. So this is the buck converter circuit. Now we are integrating both the circuit into the single topology. Similarly, the same concept I already mentioned, we have a different mode of operations here. Again, you have two switches in the previously. We have two switches here. So first we move on to the mode 1. We are going to turn on S1 and turn off the S2. So before the start of the mode 1, L1 is stored in the previous mode. So now we are going to turn on the S1 and turn off the S2. Now the input and again L1, now the diode is also conduct and the capacitor also charges up to the supply voltage. So now inductor start to decreases. Again, the L2 is charging and the capacitor C02. Again, this is the current flow. The capacitor C01 is also releases the energy through the load. Then we can write down the expressions. So what is the V0 relation and what is the inductor current I in? I in may be like this is the one of the node. You can apply for a Kirchhoff's current law. So input current is equal to inductor current plus diode current. Then from that you can write down that inductor current is equal to I in minus ID1. Similarly, here IL2, you can write down that capacitor current. IL2 can be written as IL1 because this is IL1. So IL1 plus IC1. Then after combining these two, we can express. So IC1 plus IL1. Here there is a node. Again, the output current is like IL2. So we are going to return the expression. Here V02. Again, this is the input voltage. So applied voltage, you can apply for the Kirchhoff's voltage law. Applied voltage is equal to your applied voltage is V, potential rise is V in. Then remaining you can write down the potential drops. Then from the we have a VL1 and a VL2 and then again a V02. So from that you can write down V02 is equal to V in minus VL1 minus VL2. Then we are written this is the expression. Similarly, in the mode 2, we are going to close the both the switches. Now these inductors, previous mode fully discharged. Now once it discharges, then L2 is charges in mode 2, mode 1. In mode 2, we are going to turn on the S1 and the S2. Now we are going to now the inductor L1 is start to charge. So this is the direction. Again, so now the diode is off conditions. Now the current circulate like this, the inductor current. So again, we have to write down the V naught 2 is also equal to what? So there is a minus polarity here, minus voltage across. Whatever the voltage available here, it is equivalent to like voltage across the inductors. Similarly, IL2 current is also equal to what is the current through the capacitor, and I naught. I naught is equal to V naught 2 by load resistance. So similarly, VC1 is also equal to voltage across the inductor. So bigger diode is in on condition. So whatever the capacitor VC1, it is equal to the voltage, but because both are connected in parallel. So therefore all are, so this is equal. So inductor also charges up to the inductor L1 is charges up to the supply voltage. So therefore voltage similarly the inductor and capacitor both are parallel. Diode is on condition. So inductor and capacitor both are charges up to the supply voltage like input voltage level. So this is the mode 2. Similarly mode 3, again we are going to open the switch 2. Now previously mode inductor stored the energy. Again now it is the releasing the energy. This is the mode 3. Again mode 4, we are going to open the both switches. When we are going to open the both switches, the diode, because the capacitor energy is fully discharged. Now the inductor energy and capacitor, now this diode is reverse biased, inductor, input voltage, all put together connected to the load through the diode D2. Now the capacitor C01 is start to charge. At the same time, the inductor also releases the energy through the freewheeling diode here. This is the buck operation. This is the superlift converter operations. Now we can write down the mathematical relation according to the circuit. So this is the one more equation. Again, the first step up converter, the inductor L1 is storing the energy and releasing the energy. Then after equating the volt second balance equations, you will get the V naught 1 by Vn is equal to 2 minus D2 by 1 minus D2. D2 is a duty cycle of the switches 2. Similarly for a step down converters, so V naught 2 by Vn is equal to D1 minus D2 divided by 1 minus D2. So this is the another circuit. So another topology, another circuit of multi-port converter. So the first one, what we have discussed here, boost converter, normal fundamental boost converter, how we are integrated into buck converter. Next one is superlift, normal superlift converter, we are going to integrate it into buck converters. So the next one is another topology that is called as Shepherd-Taylor converters. So what do you mean by Shepherd-Taylor converter is this is also one of the soft switching converters. The Shepherd-Taylor converter concept as proposed by D.I. Shepherd and B.E. Taylor in 1983 for achieving high power factors and output voltage regulation of the AC to DC based buck boost converter operations. Now, I hope everyone knows about soft switching techniques. We need to reduce the switching losses. Okay, so now we can achieve for a good efficiency. That's why we go for the soft switching concept. When you go for a soft switching concept, there are zero voltage switching and zero current switching. So now zero transient switching. So now when you go for a zero current and zero voltage, so we can add for the tank component like storage, like resonant component like inductor and capacitors. So based on that, we can say like zero voltage switches and zero current switches. Right. So now we can do for a zero voltage normal switch, we can convert it into zero voltage switching means we can add inductors and capacitor combinations. Similarly for a zero current also. But we are doing for a separate concept for a zero voltage and zero current. When you go for the Shepherd-Taylor concept, we can do the zero voltage switching and zero current switching in the single circuit itself. That is the one of the speciality and the advantages of the Shepherd-Taylor converter. We don't do for the zero voltage switching separately, zero current switching separately. We can combine we can do both in a single circuit itself. That is the one of the advantages for the Shepard-Taylor converters. So when you go for this, so this is the structure. This is the structure of the Shepard-Taylor converters. We need for two switches, two diodes, and capacitor. For example, normal boost converter. In normal boost converter, you have a switches. Just instead of that single switch, you can replace it and then you can insert this concept. Now we are going to call it as a Shepard-Taylor boost converter. Similarly, you can apply for the normal loop converter or single-ended primary index FE converter or buck boost converter, or you can apply for any type of DC-DC converters or any power converters. Just you can replace for the normal switch into this switch, but based on that working, you can also arrive the expression. That is very important. We will discuss one by one. Okay. Now, next thing is when you go for this type of circuit, so naturally what will happen, we don't have any voltage stress and current stress di by dt and dv by dt. Here we don't use, we are also able to avoid further. When you go for the zero voltage switching and zero current switching concept, we are going to use for the tank component. Okay, we can use for the, we can use some tank component like LNC. But coming to here also, normally I want to reduce for the dV by dt. What we have to do means we can use some snubber circuit, like you can connect R and C across the switches to reduce for the dV by dt. Similarly, for di by dt, you have to connect for the inductor in series with the switches. But here for this circuit structure, when you are added to the any type of circuit or converters, so we are avoiding for a snubber circuit. So this tank component is forcing our voltage and current of power devices at zero conditions. So that is another advantages. So if you reduce the switching losses, normally efficiency going to be high, and also you can get the good output voltage regulation for different input voltage through the closed loop control. Then we can have a minimum number of components for when you are going to implement this type of structure to the any type of circuit. Here we can have a, how to achieve the zero voltage switching and zero current switching is, here two switches are there. When we are going to turn on the main switches, so when we are going to turn on this S1 and S2, so that time we can observe the current waveform. So now we can achieve for the zero current switch. When we are going to open the, that means the turn off the diode D2 and D1, so that time we can achieve for the zero voltage switching. So, so by using this structure, we can attain for a zero voltage and a zero current. So when the two switches are in on conditions, we can attain for a zero current switching. When the two diodes are in off conditions, we are attain for the zero voltage switching. Next, another one more advantage, we don't use for additional any input side filter to reduce for the ripple current. So the proposed converter itself to minimize the ripple current. We can also operate our within the low duty cycle itself. We can obtain for the high level of output voltage by using this type of topology. So these are all the main benefit of Shepard-Taylor converters. When you go for EV charge applications, we can use this type of circuit. Now I already mentioned. So this is the one of the Shepard-Taylor boost converter. I hope everyone knows about the conventional boost converter. In conventional boost converter, you have a input voltage and then inductors, and again you have here one switch here. Okay, so again you have diode here, next capacitor, and then load resistance. Now instead of the single switch, so we are going to use for this concept. Now we are inserting the Shepard-Taylor structure here. This is the Shepard-Taylor structure. It consists of two switches and two diodes and on tank component like resonant capacitors, right? So now we are inserting conventional boost converter. You have switch. Instead of that single switch, we are inserting the two switches and two diodes and one capacitor, that is a tank component. Now we are converted conventional boost converter into Shepherd-Taylor boost converters. Now here the load you can connect for the battery. So you can connect the battery applications for charging applications here. Now move on to the working of the circuit here. So what is the working concept for the circuit is, uh, first we have to close the two switches Q1 and Q2. So before start of the mode also, this L1 previously stored the energy. So therefore, what will happen when we are going to turn on the Q1 and Q2? So now these inductors start to decrease again, then supply voltage again connected to the circuit. The inductor previous mode, it store the energy. So when we are going to turn on the Q1 and Q2, the inductor start to decreases. Then input voltage also connected to the capacitor. Now the capacitor start to charging. So these are the current directions. Okay, so once this capacitor voltage reaches to the output voltage, that time the diode D3 is conductor. Now the capacitor start to charge, but it is not reaches to the output voltage. So because now the capacitor C2 start to discharge here. Okay, so next mode, next mode. So we have three mode of operation here. As per the Shepherd-Taylor converter concept concern, there are three mode of operation. But normal conventional boost converter, you have only for two mode of operations, right? Here we can go for the mode 2. Now we are going to open when we are going to turn on the Q1 and Q2, then you can just see the current waveform. So the current waveform, there is no voltage stress here. So now we are going to achieve for the zero current switching. Next, here the two diodes are off conditions. We can also achieve for the there is no voltage stress. So now we can also achieve for the zero voltage switching. Next, we are going to mode 2. Q1 and Q2 both are in off conditions. So now what will happen? So now the inductor start to charge. Inductor start to charge here. Again, the capacitor also charging here. This is the conditions. Next is again Q1 and Q2 of conditions in mode 3. Then now the capacitor is equal to C1 is equal to our output voltage. So now what will happen? When the capacitor C1 is reaches to the output voltage, now the diode D3 start to conduct. So input voltage plus inductor connected to the load. So this is the mode 3 operations. Now these are all the output voltage. For example, input voltage is 25 volt to 48 volt. Then the output voltage 200 volt. So the input voltage 25 to 48 minimum voltage of input we can attain for the 200 volt output. So by using this circuit. So now the output current is also varies from 0.5 to 5 amps. Duty cycle varies from 0.38 to 0.44. So for minimum duty cycle, we are obtaining the good high level of output voltage by using this type of circuit. So this is more suitable for EV applications also. So now move on to the another type of converters. Uh, we can go for multi-level DC-DC converters. Here, multi-level cascaded DC-DC converter is, we can take a conventional converters. Now this is called as a synchronous buck converters. Normal buck converter we used as a diode. Here we are going to use for the diode, but in synchronous buck converter we used as a switches here. Now we can cascading for just connect for series combination. So here you can have a 12 volt, for example, maybe here maybe a 20 volt output, 20 volt output, and so total you'll get output is 60 volt. So this is also another way we are generating the more voltage at the output side by using a DC-DC converter. So this is also in the input side we can use for some PV, maybe solar panel, renewable applications. We can use for fuel cell or you can use for the super capacitors. So you can charge the EV battery. Or this is the another circuit topology. Now here I have developed one of the Blue converter into Shepherd-Taylor converters. Now normal, this is a negative output superlift loop converter. So now here you have a single switch. So that single switch I can replace it into the Shepherd-Taylor concept. Two switches, two diodes, one capacitor. Again, the remaining component are structure of the superlift to loop converter. I already told, so before start of the mode 1, this inductor is already stored. So therefore S1, Q1, S1, S2 on, the inductor again, the capacitor again D2, then connected to the circuit. Now C1 is start to charge. At the same time here low potential, therefore D4 is off condition. Capacitor C3 also discharging. Next again, we are going to open the two switches. Now the diodes are conduct again, the input again, now the inductor start to charge. So once this capacitor C1 is reaches to the output voltage, this diode D4 is start to conduct. So therefore this start to conduct, D3 is off conditions. So this is the working for the negative output Shepherd-Taylor loop converters. So normal loop converter I converted into Shepherd-Taylor loop converters. Now this is the best simulated results. So now given as input voltage is 12 volt, the output voltage is a negative output voltage. So minus 333.33 volt. So now 12 volt input, then the output is minus 333.33 volt. We are going to obtain. So now minimum voltage, minimum input voltage, low input voltage, we can obtain for a high output voltages. Then the ripple will be minus 0.1 volt. You can see the voltage across the switch here. This is for a zero voltage, zero current switching and zero voltage switching. See the current waveform. So there is no, during the on time and off time, so current and current also crossing when the device is on and device is off, then the current waveform is crossing to zero. So we are achieving for a zero current switching. Here also we have a zero voltage switching. Just see here also during the turn off time and then switch, then we are achieving for the zero voltage switching. So now this is the controller. So when you choose some PI control also, we are implemented in the negative output Shepherd-Taylor converters. By using a Ziegler-Nichols tuning method, we are obtain the proportional gain value and integral value. First, we have to do the mathematical modeling of a negative output Shepherd-Taylor based converter using a state-based average model. Based on the mathematical modeling, we converted into transfer function. That transfer function we applied to some step response input. Based on the observation of the output response, we have a sustained oscillations, then we can go for the Ziegler-Nichols tuning method 2. Then based on the Ziegler-Nichols tuning method 2, we obtain the values of KB and TI values for the negative output elementary superlift loop converter based Shepherd-Taylor converters. Now here we have the voltage regulation. Output is always maintained constant by changing the different input voltage like 12 to 15 volt and 15 to 12 volt during the line variations. The second one is second one. So below the figure right, we have one waveform. This is called conventional superlift loop converter. In conventional superlift loop converter, the same input voltage is 12 volt. The output is minus 30, 33 or 34 point or some voltage. But when you go for Shepherd-Taylor converter, input is 12 volt, output is minus 333.33 volt. So this much of deviation is between the Shepard-Taylor converter and normal. So I already told why we go for this type of converter to increasing the voltage transfer gain and also reducing the ripples. Minimum duty cycle we can operate at a high level of voltage. So this type of circuit is more suitable for EV charging applications. Thank you. If you any doubt, please ask me. Thank you.
Thank you, sir. Participants, any queries?
Thank you, sir.
So participants can ask their queries. Okay. Shall I conclude, sir?
Okay. Thank you.
Okay, thank you very much, sir, for your nice presentation. You detailedly explain about the multi-port converters and drawbacks of the two converters for the low voltage and high voltage in the inside the electric vehicles, and clearly explain about the integration of super lift converters with the buck converter. And last, you clearly explain about the Sheffer-Taylor converter and zero voltage and zero current switchings. You detailedly explain about the analysis as well as the results. Thank you very much, sir.
Thank you. Thank you.
So participants, your feedback will be posted in your chat box. So do fill the feedback. Again, I told you 80% of attendance as well as the filling of the feedback and the final assessment is required to get your e-certificates. Thank you. Thank you, Ramesh Kumar, sir. Now we can leave, sir. So participants, fill the feedback form in the posted in the chat box. Besar kalau dalam No.
Sir, shall we quite, sir?